Welcome to the fascinating world of quantum physics, where the boundaries between waves and particles blur. In this chapter, we explore the dual nature of radiation and matter, a concept that revolutionized our understanding of the microscopic world. From the mysterious photoelectric effect to the groundbreaking experiments that confirmed wave-particle duality, we'll journey through the key discoveries and principles that shape modern physics. Let's begin by setting the stage for why the dual nature of matter and radiation is so crucial in quantum mechanics, and how it challenges the classical views that dominated science for centuries. Photoelectric effect is a phenomenon where electrons are ejected from a material, usually a metal, when it is exposed to light of a certain frequency. This effect could not be explained by classical physics, which predicted that light's energy depended only on its intensity. Instead, experiments showed that only light above a certain frequency could release electrons, regardless of intensity. This observation hinted at a deeper, quantum nature of light, suggesting that light behaves not just as a wave, but also as a stream of particles called photons. Photoelectric effect follows certain laws observed through experiments. First, no electrons are emitted if the incident light's frequency is below a threshold, regardless of intensity. Second, the number of emitted electrons is proportional to the light's intensity, provided the frequency is above the threshold. Third, the kinetic energy of emitted electrons depends on the light's frequency, not its intensity. These laws pointed to the quantum nature of light and set the stage for Einstein's revolutionary explanation. Albert Einstein explained the photoelectric effect by proposing that light consists of discrete packets of energy called photons. Each photon carries energy proportional to its frequency. When a photon strikes an electron in a metal, it transfers its energy to the electron. If this energy exceeds the work function of the metal, the electron is ejected. Einstein's equation, Ke equals hf phi, where Ke is the kinetic energy of the electron, h is Planck's constant, F is the frequency, and phi is the work function, elegantly describes this process. Measure the maximum kinetic energy of photoelectrons. Scientists use the concept of stopping potential. This is the minimum voltage needed to stop the fastest emitted electrons from reaching the collector plate in a photoelectric experiment. By applying this voltage, the kinetic energy of the electrons is counteracted, and the relationship EV0 equals Kemax is established, where E is the electron charge and V0 is the stopping potential. This method provides a direct way to measure the energy of photoelectrons and further supports Einstein's theory. Work function is the minimum energy required to remove an electron from the surface of a material. It is a characteristic property of each material and plays a crucial role in the photoelectric effect. If the energy of the incident photon is less than the work function, no electrons are emitted. Only photons with energy equal to or greater than the work function can liberate electrons, making this concept central to understanding how materials interact with light at the quantum level. Photoelectric effect was experimentally verified using setups where light of varying frequencies and intensities was shown on metal surfaces. Detectors measured the emitted electrons and their energies. These experiments consistently showed that electron emission depended on the frequency of light, not its intensity, confirming Einstein's predictions. Such verification was pivotal in establishing the quantum theory of light and demonstrated the limitations of classical wave theory in explaining these results. Wave-particle duality is the concept that every particle or quantum entity exhibits both wave and particle properties. Light, for example, can behave as a wave, showing interference and diffraction, but also as a particle, as seen in the photoelectric effect. This duality is not limited to light. Matter, such as electrons, also displays wave-like behavior under certain conditions. This idea fundamentally changed our understanding of the nature of reality at the smallest scales. De Broglie proposed that not only light, but all matter has a wave nature. According to his hypothesis, every moving particle is associated with a wavelength, now known as the de Broglie wavelength. This bold idea extended the concept of wave-particle duality to electrons and other particles, suggesting that the quantum world is governed by principles far different from classical physics. The de Broglie hypothesis paved the way for new experiments and theories in quantum mechanics. De Broglie wavelength expression mathematically relates a particle's momentum to its wavelength. The formula is lambda equals hp, where lambda is the wavelength, h is Planck's constant, and p is the momentum of the particle. This equation shows that the wavelength is inversely proportional to momentum. The faster or heavier the particle, the shorter its wavelength. This relationship is fundamental in understanding the wave-like behavior of matter at the quantum scale. Davison-Germer experiment provided direct evidence for the wave nature of electrons. In this experiment, a beam of electrons was directed at a nickel crystal, and the scattered electrons formed a diffraction pattern, similar to what is seen with light waves. This result confirmed de Broglie's prediction that particles like electrons can exhibit wave-like behavior, marking a major milestone in the development of quantum mechanics. significance of the Davison-Germer experiment lies in its confirmation of the wave nature of matter. Before this experiment, wave-particle duality was mostly theoretical. The observed electron diffraction pattern provided concrete, experimental proof that particles can behave as waves. This discovery validated de Broglie's hypothesis and forced physicists to rethink the fundamental nature of particles and waves, leading to the birth of quantum mechanics. Electron diffraction is a phenomenon where electrons, when passed through a crystal or a thin film, create a pattern of constructive and destructive interference, much like light waves. This effect is a direct demonstration of the wave-like nature of electrons and other particles. Electron diffraction is used in various scientific techniques to study the structure of materials at the atomic level, providing insights into the arrangement of atoms and molecules. Matter waves, also known as de Broglie waves, refer to the wave-like behavior exhibited by particles such as electrons, protons, and even atoms. According to quantum theory, every moving particle is associated with a wave, and this wave determines the probability of finding the particle at a particular location. Matter waves are central to quantum mechanics and are essential for understanding phenomena like electron diffraction and quantum tunneling. Broglie waves have numerous applications in science and technology. They are fundamental to the operation of electron microscopes, which use the wave nature of electrons to achieve high-resolution imaging of tiny structures. De Broglie waves also play a role in quantum computing, nanotechnology, and the study of atomic and molecular structures. Their applications continue to expand as our understanding of quantum mechanics grows. Uncertainty principle is a fundamental concept in quantum mechanics, stating that it is impossible to simultaneously know both the exact position and momentum of a particle. This principle, introduced by Werner Heisenberg, highlights the inherent limitations in measuring quantum systems. The more precisely we know one property, the less precisely we can know the other. This uncertainty is not due to experimental errors, but is a fundamental property of nature. Heisenberg's uncertainty principle mathematically expresses the limits of precision for certain pairs of physical properties, such as position and momentum. The principle is often written as deltax delta greater or equal to, where deltax is the uncertainty in position, delta is the uncertainty in momentum, and h is Planck's constant. This relationship means that increasing the accuracy in measuring one quantity leads to greater uncertainty in the other, a core idea in quantum mechanics. Let's derive the uncertainty relation for position and momentum. According to quantum mechanics, the product of the uncertainties in position, deltax, and momentum delta of a particle is always greater than or equal to a constant. Specifically, this means that if we try to measure a particle's position very accurately, its momentum becomes highly uncertain, and vice versa. This principle is a direct consequence of the wave-like nature of particles. Similarly, the uncertainty principle applies to energy and time. The uncertainty in energy, delta, and the uncertainty in time, delta, are related by the expression delta delta greater or equal to. This means that the more precisely we measure the energy of a system, the less precisely we can know the time interval during which that energy is defined. This relationship has profound implications for the stability of quantum systems and the behavior of particles at very small scales. Classical physics, which includes Newtonian mechanics and Maxwell's electromagnetism, could not explain phenomena like the photoelectric effect, blackbody radiation, and atomic spectra. These failures highlighted the need for a new framework, quantum mechanics. The limitations of classical physics became clear as experiments revealed behaviors that could only be described by considering the dual nature of light and matter and the probabilistic nature of quantum events. Dual nature of matter is a cornerstone of quantum physics. It explains why particles can behave like waves and vice versa, leading to phenomena such as interference, diffraction, and tunneling. Understanding this duality is essential for grasping the behavior of atoms, molecules, and subatomic particles. It also underpins the development of technologies like lasers, semiconductors, and quantum computers, making it one of the most important concepts in modern science. For quantum theory, light was primarily understood as a wave, capable of interference and diffraction. Experiments like Young's double-slit experiment demonstrated these properties, showing that light could create patterns characteristic of waves. This wave description explained many optical phenomena, but could not account for the photoelectric effect or blackbody radiation, hinting at a more complex nature of light. Discovery of the photoelectric effect revealed that light also behaves as a particle. When light of sufficient frequency strikes a metal surface, it ejects electrons, a process that can only be explained if light consists of particles, or photons, each carrying a specific amount of energy. This particle-like behavior was a key piece of evidence for the quantum theory of light. Max Planck introduced the idea that energy is quantized, meaning it can only be absorbed or emitted in discrete amounts called quanta. This hypothesis explained blackbody radiation and laid the groundwork for quantum mechanics. Planck's constant, h, became a fundamental constant in physics, appearing in equations that describe the energy of photons and the wavelength of matter waves. Photons are the quantum particles of light, each carrying energy proportional to its frequency. Unlike classical particles, photons have no mass and always travel at the speed of light. The concept of photons is essential for understanding phenomena like the photoelectric effect, Compton scattering, and the emission and absorption of light by atoms. In quantum mechanics, energy is quantized, meaning it exists in discrete levels rather than a continuous range. This concept explains why atoms emit or absorb light at specific wavelengths, leading to the characteristic spectra of elements. Energy quantization is a direct consequence of the wave-particle duality and the mathematical framework of quantum mechanics. Threshold frequency is the minimum frequency of incident light required to eject electrons from a material in the photoelectric effect. If the light's frequency is below this threshold, no electrons are emitted, regardless of the light's intensity. This concept is crucial in distinguishing quantum behavior from classical predictions, as classical theory could not account for this frequency dependence. In the photoelectric effect, increasing the intensity of light increases the number of emitted electrons, but does not affect their kinetic energy. Only increasing the frequency of light above the threshold increases the kinetic energy of the electrons. This observation directly contradicts classical wave theory and supports the quantum model of light. One of the striking features of the photoelectric effect is the instantaneous emission of electrons when light of sufficient frequency strikes the material. There is no measurable delay, even at low intensities. This immediate response could not be explained by classical theories, which predicted a time lag for energy accumulation. The quantum explanation, involving photon absorption, accounts for this instant emission. Typical photoelectric experiment involves a vacuum tube with a metal plate as the emitter and a collector plate. Light of varying frequency is directed onto the emitter, and the resulting current is measured. By adjusting the voltage between the plates, scientists can determine the stopping potential and study the kinetic energy of the emitted electrons. This setup has been crucial in verifying the predictions of quantum theory. Planck's constant, denoted by h, is a fundamental quantity in quantum mechanics. It appears in equations describing the energy of photons, E equals hf, and the de Broglie wavelength, lambda equals hp. The small value of Planck's constant explains why quantum effects are not noticeable in everyday life, but become significant at atomic and subatomic scales. Wave nature of electrons was confirmed by experiments like Davison-Germer, where electrons produce diffraction patterns similar to light waves. This wave behavior is described by the de Broglie wavelength and is essential for understanding phenomena such as electron microscopy and quantum tunneling. The realization that matter can behave as a wave was a major breakthrough in physics. Quantum tunneling is a phenomenon where particles pass through energy barriers that would be insurmountable according to classical physics. This effect is a direct consequence of the wave nature of particles and is essential in processes like nuclear fusion in stars and the operation of tunnel diodes in electronics. Quantum tunneling demonstrates the non-intuitive, probabilistic nature of quantum mechanics. In quantum mechanics, the behavior of particles is described by probability waves. The square of the wave function gives the probability of finding a particle at a particular location. This probabilistic interpretation replaces the deterministic predictions of classical physics and is a direct result of the wave-particle duality. Quantum physics differs from classical physics in fundamental ways. While classical physics describes the world in terms of definite positions and velocities, quantum mechanics deals with probabilities and uncertainties. The dual nature of matter and the uncertainty principle are key features that distinguish quantum theory from its classical counterpart. Wave packet is a combination of waves of different wavelengths and frequencies used to describe particles in quantum mechanics. Wave packets allow us to localize particles in space, but also introduce uncertainty in momentum. This concept is essential for understanding the spread and localization of quantum particles. In the context of matter waves, group velocity refers to the speed at which the overall shape of the wave packet moves, while phase velocity is the speed of individual wave crests. For particles, the group velocity corresponds to the particle's actual velocity. Understanding these velocities is important for analyzing the motion of quantum particles. Electron microscopes utilize the wave nature of electrons to achieve much higher resolution than optical microscopes. By using electrons with very short de Broglie wavelengths, these instruments can image structures at the atomic level, revolutionizing fields like biology, materials science, and nanotechnology. Quantum computing harnesses the principles of quantum mechanics, including superposition and wave-particle duality, to perform computations far beyond the capabilities of classical computers. Quantum bits, or qubits, can exist in multiple states simultaneously, enabling new algorithms and applications in cryptography, optimization, and simulation. Nanotechnology relies on the quantum behavior of matter at very small scales. The wave nature of electrons and atoms is essential for designing and manipulating materials at the nanoscale. Applications include advanced electronics, medical devices, and new materials with unique properties. Study of atomic and molecular structure is deeply rooted in the principles of quantum mechanics. The arrangement of electrons in atoms and molecules, their energy levels, and the formation of chemical bonds all depend on the wave-particle duality and quantization of energy. These principles explain the periodic table and the behavior of elements. Quantum tunneling is not just a laboratory phenomenon. It occurs naturally in processes like nuclear fusion in stars, where protons tunnel through energy barriers to combine and release energy. This process powers the sun and is essential for life on Earth. Tunneling also plays a role in radioactive decay and enzyme reactions in biology. Modern technology is deeply influenced by quantum mechanics. Devices like lasers, transistors, and semiconductors rely on quantum principles. Understanding the dual nature of matter and radiation has enabled the development of computers, smartphones, and countless other innovations that shape our daily lives. In summary, the dual nature of radiation and matter is a foundational concept in quantum physics. It explains phenomena that classical physics could not, such as the photoelectric effect and electron diffraction. The principles of wave-particle duality, uncertainty, and quantization have revolutionized science and technology, opening new frontiers in research and innovation. As we continue to explore the quantum world, the dual nature of matter and radiation remains at the heart of new discoveries. From quantum computing to advanced materials, the principles discussed in this chapter will continue to shape the future of science and technology. Stay curious and keep exploring the wonders of quantum physics.